Welcome. This is Dr. Morton, and I'm going to cover Chapter 5 today in Logic Design. So let's get started. Okay, so here we are in the book, and you can see what we're going to cover today is depicted in this picture here. We're going to start with this table that we call a truth table. Notice it has A, B, C, and F at the top. A, B, C are the independent variables, and F is the output. So we have various combinations of A, B, C, or A prime, A and A prime, B and B prime, C and C prime going into these various AND gates in the case of a SOP solution, and they feed into one output OR gate, and out of there comes F. And this is what we're going to work on today. How you take this and you can actually come up with the logic expression that you can then turn into hardware. All right. So I did want to go through the learning objectives. I would like students, when we finish this, to be able to demonstrate how to write the min-term expression and the max-term expression for each row of a 3 or 4 variable truth table. I'd like you to also understand how a truth table can be implemented as a min-term expression and as a max-term expression, and which is kind of redundant, I guess, for the top one there. And next, I want you to understand how to basically write this as our standard sum of products form or our standard product of sums form. These are the same. The SOP is the min-term expression, and the POS is the max-term expression. However, normally we're going to simplify our initial expressions to get them in the final POS or SOP form. And then I'd like you to understand what an incompletely specified truth table is and how we use the rows that are not specified, which we call don't cares, how those can be helpful to the designer, why we need to take those into account. And finally, I want to teach you the shorthand notation for the SOP and POS forms, or the min-term and max-term forms, however you want to call them. And we'll show you that shorthand notation, which we'll generally use in the rest of the course. In the rest of the course, when we say the SOP or POS notation, or we might say the min-term or max-term notation, we want you to use the shorthand. When we say we want you to write the min-term or max-term expression, that means we want you to write out the actual logic equations with all the variables. And we'll show you that difference. All right. Again, we have glossary terms where you can see we have, they highlight as you hover over them. All right. First, we're going to look at a template that is really not a truth table, and that's this figure 5.1. This is really a contrived device, and what it shows is a 3-variable template and the min-terms and max-terms associated with that template, without any output function being specified. So there is no column for F for the output function. So we have ABC, and we have all possible combinations of ABC. Remember, if you have 3 independent variables, then you will have 2. So that's n independent variables, where n equals 3. So that's 2 to the n, or 2 cubed, which is 8. There are 8 rows. If we had 4 variables, we'd have 16 rows. So it always works out to be 2 to the n, where n is the number of independent variables. For each output function, we'll have to have an additional column. In this case, we do not have a function specified. But what we do have specified is the min-term and the max terms associated with every row. So for min-term row 0, which we call min-term 0, that would be A prime, B prime, C prime for a 3-variable truth table. And min-term 7, and again, we don't call this row 8, we call it row 7 because we always start by numbering the first row 0, then 1, 2, 3, 4, 5, 6, 7. Min-term 7 is going to be A, B, C, and all the various ones in between. So you notice min-term for row 1, because A is 0, B is 0, and C is 1, this is called A prime, B prime, C. where C isn't primed, but A and B are because they're both 0, but C is 1, so it's not primed. Here, 3 zeros, they're all 3 primed. Here, 3 ones, they're all non-primed. And that's how you do the min terms. The max terms are very similar, except instead of anding these variables together, we're ORing them together. And instead of having the zeros be primes, the ones are primes and the zeros are not. So here, max term for row 0 is going to be A plus B plus C. Max term for row 7 is going to be A prime plus B prime plus C prime. And again, that's these ORed together. Okay, now I wanted to say one more thing about when we have a column for F, which we will in all of our truth tables from this point on. This template, this is the only time we're going to look at this template, and we're never going to look at it again. Well, you can go back and look at it if you want, but in any event, we're not going to put these columns in. You're just going to have to be able to look at the independent variables and figure out for each row what the min terms and max terms should be. Again, like for instance here, we have A is 1, B is 0, C is 0, so the min term is A, B prime, C prime, and the max term is A prime plus B plus C. So a little bit of practice, you'll be able to do this quite easily for every row, and we won't have to provide this green column and this red column again. But in every truth table, we will have a column for F. Now, a lot of students are confused about where F comes from. F comes from your customer. It's the problem you're given as the engineer to go out and design a circuit to solve. So your circuit is going to provide the correct output, the correctly specified output for F for every combination of input variables. And how do you figure out what that is? Well, it depends on what the customer wants. And in some cases, that will vary for every problem. So we get the desired values for F come from the customer, or sometimes I use just to make a point, because this confuses students. The values for F are given to you. They come from God, where your customer is basically God, okay? Or at least for purposes of your professional working. All right. First, we're going to talk about how we would come up with the F. Now, does the customer actually give us the truth table? Well, usually not. Usually what the customer does is describe in English language statements what they want, and we have to translate that into the truth table. But it still comes from the customer. And if we make a mistake in the translation, then we're going to make a mistake in our hardware, because it's not going to do what the customer wants if the truth table doesn't reflect what the customer wants. And because once you put the truth table together and you have specified the value for F for every row, then you set it in cement. And as long as you do your job correctly, the circuit you come up with will deterministically create the right value for F for every single row. So if the truth table is wrong, your hardware is going to be wrong. And there's no wiggle room here. There's no maybes or almost or might be's. Whatever you specify for F, when you do your design correctly, will appear with that combination of input variables. Okay, so let's look a little bit here to begin with at how we can turn a customer's English language description into a truth table. All right, or into a logic expression in this case. And then that we'd have to translate into a truth table. We sort of work backwards a little bit. All right, so here we go. So in this case, we were given a problem. It's a simple alarm system, and I'm gonna draw that out. So here we have our simple alarm system. We have an office where we have a chair and a desk, and we have a person sitting in that chair, working on their desk, and hopefully they have a smile on their face. Okay, now we have a door, and we'll label the door D. There's a sensor on that door, and that sensor will give us a say positive 5 volts, or a 1 if it's open, and 0 if it's closed. the window is going to give us a 1 if it's closed, which is maybe a little backwards, but anyway. And I think I did the door right. So the door, door is 1 if it's open. So the window is going to be 1 if it's closed. And if it's not closed, then W is going to be 0, which means W prime would be 1. All right. Now, we also have a switch. We'll put a switch on the wall here. And if that switch is, so we'll call that a switch. And it's the master alarm switch. It's actually a master switch. So we're going to call it an M. And master switch. And then we also have some kind of a device that's a siren. And we'll call that is going to be S. All right. So here's the description. So the siren S will and when it equals 1, it's sounding. Okay. So S is going to equal it'll be sounding if and only if the master switch is on. So M equals 1. M, and the door is open. So that's going to be D, because D equals 1 is open. Or it's after, oh, I forgot, there's also a clock. And we're going to say we're going to use E here for earlier than 9 p.m. So if E equals 0, then it's less than 9 p.m. Or if E prime equals 1, it's less than 9 p.m. So we have the master switch and the door is open, or it's after 9 p.m., E prime, and the window is not closed, W prime. Now, when we have not in the name, we usually want to use primed variables. When we don't have not in the description, we usually want to use unprimed. Doesn't really matter. It all works out the same. Just depends on how we define them. All right, so here is the logic expression that we've deduced from this equation. Now, this is a little bit tricky. And so what are our independent variables? And what are our dependent variables? Well, S is our dependent variable, so that would be our output. And we have 4 independent variables: the master switch, the door sensor, the clock, the timer, and it's thresholded at 9 p.m. and then our window. So when the window is closed, it's going to equal 1. And if it's so W prime would be 0. And if our master switch is off, or if the door is closed, then D is going to be 0. So if the door is closed, regardless of the master switch, or if the master switch is off, if it's before 9 p.m. and if the window's closed, either way, then the siren won't sound. But if the master switch is on and the door is open, or if it's after 9 p.m. and the window's open, the siren will sound. Now you look at this, and the first thing you want to do is make sure that your customer is going to get what they want. And so as a good engineer, you should look at this and you should say, well, to your customer, what if you're working in the office late, but it's after, let's say it's 9:30 in the evening, and it's hot, and you want to open up the window. So you go over and you turn off the master switch, and then you open the window, but the alarm still rings. Well, why would that be? Well, it's because you have this OR right here. So you can forget this term. If this term is a 1, the siren's going to ring. Well, what would make this term a 1? After 9 p.m. and an open window. So you ask your customer, so is that what you want to happen? And the customer goes, no, I'd like to be able to turn the master switch off and keep the alarm from ringing even late at night. If I want to open the window, I'd still like the alarm to not ring if the master switch is off. So what the customer really wanted was S equals M ANDed with D plus E prime W prime. And then everything's going to work like it should, because we've used parentheses here and we put the master switch as a required component for the alarm to ring. So you can see one of the things we want to do, there's a little ambiguity in our English language statements, and we want to root that out, because in our logic expression there's no ambiguity. It's hardwired. You are going to get exactly what you write in your logic expression. No ifs, ands, or buts about it. So you as a good engineer, you want to ask those questions and make sure that you're giving the customer what they want. Okay, so that's one important point. All right, so you can have several different output equations. You want to make sure you get it right. And here's several different ways you can look at this. But the one that's probably correct is number 4 down. Well, I don't know. I didn't even write number 4. I separated the E out, so who knows. But anyway, so there's a bunch of different ways to do this, and you could actually read through my description. Okay, min-term solution. Here's a truth table. A, B, C are independent variables and an output F. So for when A and B and C are all 0, we want the output F in this particular case to be 1. Now this isn't the same problem as our window problem, as our alarm system. We haven't really described what this problem is. We've just been given this F. It came from God. We're really not going to argue about it. We're just going to write it in, and we're going to build a circuit to deliver this result. Okay, for min-term row 1, remember we always number the first row 0, 1, 2, 3, 4, 5, 6, and 7 for a 3-variable truth table. Okay, so we also notice for row 0, 1, 2, our F is 0. For row 3, it's 0. For 4, it's 1. For 5, 6, and 7, it's 0. So how would we implement this as a circuit? Well, what we do is we take the min-terms for row 0, row 1, and row 4. What are those? Well, we can go back to our template and figure out, but you could also do it easily. So row 0, row 1, and row 4. So we should wind up with A prime, B prime, C prime plus A prime, B prime, C plus A, B prime, C prime. And I think that was it, right? Yes, so just 3 terms. So we write that down, A prime, B prime, C prime plus A prime, B prime, C plus A, B prime, C prime, representing rows 0, 1, and 4. And we can look at that circuit, which somehow got left out. But I'm going to show you right there. You'll see, there it is. Okay. And, well, let me make it visible again. Sorry, I should do this. So notice we have 3 input AND gates and 1 output OR gate. And this, some of the OR gates are these little funky things, because that's what Windows provide. That's what Word and PowerPoint provide. Some of them I used another program that has a little better looking OR gate. But notice this AND gate has A prime, B prime, C prime. That's min-term 0. This AND gate has A prime B prime C, that's min term 1, and A B prime C prime, that's min term 4. So we have our three min terms represented by these three AND gates, each with three inputs, and they're generating an F. Now, this is not a simplified expression, but it will implement our function. We could probably simplify it, though, because I think we can look at A prime B prime C prime and A prime B prime C, and we can combine these and get just A prime B prime. So we could have A prime B prime in one AND gate, two inputs, and then the second AND gate, A, B prime, C prime, and we could completely get rid of one of the AND gates. Okay, so that was what simplification could do for us. All right, now I'm going to turn this off. Okay, so this is our truth table, this is our expression, and I just showed you the actual circuit. So let me switch over here to the paper, and I'm going to do another one. Oops. Yeah, there we go. Okay, so let's take another three-variable truth table. So we'll take our truth table here. We'll do A, B, C, and we'll do an output F. And we'll do 0, 0, 0, 0. 1, 2, 3, 4, 0, 0, 1, 2, 0, 0, 1, 2, and then 0, 1, 0, 1, 0, 1, 0, 1. And we'll divide it up into rows here so we can pairs of rows anyway to make it, well, maybe we'll do this. Make it a little bit easier to see. All right. And then we're going to assign an F. Let's just arbitrarily, we'll do 0, 1, 1, 0, 0, 1, 1. Something like that. So now we have, we want to write the expression for F. Well, so what min terms do we need? We need this min term, we need this min term, we need this one, and this one. And remember, we number these min terms 0, the rows anyway, 1, 2, 3, 4, 5, 6, and 7. And we'll put a line down there. Okay, so we need min term 1, 2, 5, and 6. So F is going to equal min term 1, A prime B prime C, plus min term 2, A prime B C prime, plus min term 5, A B prime C, and finally min term 6, A B C prime. Now, it turns out we can simplify this, and we can simplify it by using S1, where we combine terms. Let's see. Yes, so we can take these two and combine them to BC prime, because we have an A prime BC prime, and here we have an A BC prime. So the A changes, but nothing else does, so we can drop the A and we get BC prime. And then we can have these two, A prime B prime C, and A B prime C, so the A can drop and we can get B prime C. So now our final solution is this equals B prime C plus BC prime. And it turns out that's actually an exclusive OR gate with an input of B and C, interestingly enough. All right. So that's how we do solve the problem with min terms. Now we're going to look at the max terms. So how do we do the max terms? Well, so if we use the same truth table, we get 1, 2, 3, 4, 5 terms, which are max terms rows 2, 3, 5, 6, and 7. And this is our circuit. Well, let's go back and look at this table. So we want the max terms from all the rows where f equals 0. So that would be row 0, 1, row 2, 3, 5. So we want to do rows 0, 2, 3, and 5. Now, remember, this is different than the one we just worked on paper because we're using this truth table. So let me work this one out, and then you'll see that we in fact do get this as the result. All right, so we needed max terms 0, 2, 3, and 5. So f equals the max terms 0. Remember, if we go back to our template up here at the top, we know that max term 0 is a plus b plus c. We'll put parentheses around that. I'll show you this in a second. And then we need 2. So this is 0, 1, 2. So we need a plus b prime plus c. And then we need 3. So that's a, b prime, c prime. A plus b prime plus c prime. And finally we need 5. And 5 is going to be a prime plus b plus c prime. All right, so here's what we got. Minterm 0, minterm 2, minterm 3, so 0, 2, 3, and 5. A, B, C, quantity times A, B prime, C, which is 2. Quantity times A, B prime, C prime, which is minterm, max term 3. And A prime plus B plus C prime, which is max term 5. And then can we combine some terms here? Yeah, we can. We can definitely combine these two and get A plus C. Now, I don't know if we can combine anything else. Oh yeah, we can. We can reuse. You can reuse terms as much as we want. So we can use this one again and combine it with this one. We have A, B prime, C, and A, B prime, C prime. So the C drops. So we get A plus B prime. And then we need this term. Can we combine it with anything? No, we can't. So we just have to have this whole term. A prime plus B plus C prime. So our final solution, simplified, is A, the quantity A plus C times the quantity A plus B prime times the quantity A prime plus B plus C prime. All right. So that's, and so if we go down here and let's see if that was in fact what we got. 1, 2, 1, oh, 2, 3, 4, 5. Okay. 5.2. 1, 2, 3, 4, 5. I left out a minterm. So we had. Oh, somehow I used. How did I do that? All right. So let me just correct this. I don't know how I did it, but I did. 2, 3, 5, 6, and 7. I should have done 2, 3, 5, 6, and 7, and somehow I did 0, 2, 3, 5. I don't know how I did that. Anyway, I guess I did it off. I guess I mixed the one I was doing on paper with the one in the book. Okay, so this truth table, right? Oh, I guess I used this truth table maybe. Yeah, I did. That's what I used. Okay, this is the truth table I should have used. This was in the knowledge check. All right. So in this truth table, we have 0 for row 0, 1, 2, 3, 5, 6, 7. So I needed minterms 2, 3, 5, 6, 7. All right. So we'll just do it again. 2, 3, 5, 6, 7. So 2, 3, 5, 6, 7. That's what we need. And so let's just do that. So max term 2 is going to be, let's go back to the template and we'll write all those out. We'll do this as quickly as we can. All right, so max term 2, so 0, 1, 2, a plus b prime plus c. And then that's quantity, f equals, plus, times 3, so 0, 1, 2, 3, a plus b prime plus c prime, times 5, which is here, a prime plus b plus c prime, times 6, a prime plus b prime plus c, times 7, a prime b prime c prime, a prime plus b prime plus c prime. Right. Okay. So now here's what we have down here. This is our max term solution for figure 4.2, and now we can do some simplification, again using our S1 theorem. For instance, we can combine these two terms and to a plus b prime, since the c changes. We can combine these two terms, since the b changes, to a prime plus c prime. And that just leaves us this term, which we can also combine with this term. Or we can combine it with this term. So we have choices. I'll just combine it with this one to make it easy. And that would be, so we have a prime b prime plus c and a prime b prime c prime. So that just gives us a prime plus b prime. And then we can actually combine these two terms because we have an a plus a b prime and an a prime plus a b prime. So that just gives us b prime times a prime plus c. A prime plus c prime. So our final solution, we'll just write the b outside of the parentheses, times a prime plus c prime equals f. So that's our max term solution. And that's simplified, but of course our unsimplified solution would require 1, 2, 3, 4, 5 OR gates. And that's what I put in the book. So let's look at that. And it's right here. 1, 2, 3, 4, 5. A prime B prime C, A prime B prime C prime, A prime B C prime, A prime B C, and A prime B prime C prime. When we simplify it, then we reduce it to one OR gate with 2 inputs and one AND gate with 2 inputs. And that's it. So much simpler and much lower cost, because remember, cost is number of gates, number of inputs, and our timing is number of layers. And of course we still have a 2-layer network, but we had a much simpler network if we get rid of some of these gates by simplification. Okay, all right. Now I want to talk about incompletely specified truth tables. What is an incompletely specified truth table? It is so in any given truth table, let's do a little drawing here. For any given truth table, if we write out our, let's do a little truth table here. So again, we'll do one with A, B, C, and we'll have F here. And then we're going to do, so we're going to do it like this. All right, so we have 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, and 0, 1, 0, 1, 0, 1, 0, 1. Notice we always call this one that changes every row the low order variable, and this one is the high. So A is our high order variable and C is our low order. Our input variables are almost always ranked in some kind of hierarchical ranking because that's the way things work in the binary world. So we really do need to kind of keep that in mind. Okay, let's look at F. So what are we going to do for F? Well, let's say we know we want a 1 here and maybe a 1 there and a 0, and say a 1 there and a 1 there and maybe a 0 and a 1. But this row, there's something kind of weird going on with this row. Our customer tells us that A equals 0, B equals 1, and C equals 1 will never happen. Okay? When the customer tells us this is never going to happen, we can put an X here, and that X equals don't care. Now, like most things in logic design, the name that's been given to this is a little confusing. What's confusing is it's not so much that we don't care about this value. We actually do care because we want to pick it carefully to make sure it simplifies our overall equations that result in our solution. And how we pick it could allow us to simplify it more or less. So we do care about it, but what we know is that it's never going to occur, so it doesn't matter. So really it should be do care but doesn't matter for the actual output F, but it does matter for our ability to simplify our resultant network. And of course, we always want to simplify things if we can, and in some cases, carefully choosing that can result in a big simplifications. So it is important. But that's how the don't care comes into play. Now, the way you have to solve this, and we'll talk more about this, with a K-map it's easy, but if you don't have K-maps, then you actually have to do two expressions for F. You have to write an expression for F where with the don't care, and an expression for F without the don't care. So con, don't care, and sin, don't care. A little Spanish twist on that. So, and then you have to simplify those two expressions as much as you can and see which one is the simplest. And if one of them is simpler, then that tells you how you should choose the don't care. And it turns out it's almost always has an impact. It almost always makes a difference. Maybe it always makes a difference, but maybe not. And there might be some rare cases where it doesn't, but normally it does make a difference. And if you choose it poorly, then you will wind up with a more complicated circuit than you would have had if you chose it wisely. All right. And finally, we want to talk about this shorthand notation, and we're going to be done. I've gone a little longer than I wanted to, but all right. So shorthand notation. So basically, we have two forms. In our shorthand notation, we say F equals the sum of the min terms, and then we put in the numbers of the minterms. In this case, minterm 1, 4, 6, and 7. So we don't actually write out the logic expression. And if we have an incompletely specified function, then we'll add in the don't care with plus the sum of the don't cares, in this case just 1, row 5. Here we would have the same thing, only we'd use the rows where the zeros occur. So, and we use, instead of the sum sign, we use the product sign. It's the product, and instead of the little m's for min terms, we use big M's for max terms. So it's the product of the max terms, 0, 2, and 3, times the product of the don't care max term, 5. Now the don't cares are the same. But what I can tell you is that if it simplifies the minterm expression to use the don't care, then it almost always simplifies the max term expression to not use it, and vice versa. All right. With that, I'm going to quit, and we'll see you in Chapter 6.